Hi everyone, welcome to the machine learning lecture series from eGain.ai. So today in this lecture we will be looking into Perceptron algorithm. I am Dr. Amrith Krishna, your lecturer for the machine learning series. So let's have a look into the Perceptron algorithm. So linear classifiers, which are also called as linear threshold units, are defined by a weight vector W and a bias B. They operate on input vectors X and a label space of -1 and 1. Here, the input vector and the weight vectors match their dimension. So input vector as well as the weight vector both have a d-dimensional vector. They match their dimensions. Now, it takes the dot product of W transpose X. Let me repeat it. It takes the dot product between W transpose and X and add it with bias. So if the value is a positive or 0, then the label is 1, else the label is -1. And this thresholding is done by this sine function. So summarily, the dot product is basically sigma I wi xi, where I being each of the d dimensions and b being the bias term. The sum followed by the sign operation determines the label, which is either +1 or -1. This is how any linear classifier learns. So the operation that we just discussed is illustrated in the figure shown here. Dot product of W transpose and X and the summation with bias is shown here. This is x1 to xd, in this case 8. So w1 to w8 and the bias. So the linear classifier has an intuitive geometry. Linear classifier defined in a two-dimensional space has a line as it's the separator or the classifier. A plane in three-dimensional space forms the separator. A hyperplane in a d-dimensional space forms the separator. Or I should correct it by saying that a d-1 dimensional hyperplane forms the separator or the classifier in a d-dimensional space, and naturally for a two-dimensional space then a one-dimensional line forms the separator. So the hyperplane slices the instant space into two parts, one side being the positive and the other is the negative. It's the linear surface that slices the space. So in this case you can see all the positive data points. It need not always remain in the first quadrant, but just saying all the positive points and all the negative points are separated by this line, where we are assuming two features or a two-dimensional space. So those are the x1, x2 with the corresponding bits w1, w2 and the bias. So the perceptron was introduced by Frank Rosenblatt in 1958 with quite a tall claim, as you can see here, that says a probabilistic model for information storage and organization in the brain. The goal of the perceptron algorithm is to find a separating hyperplane for a given dataset represented in a certain instance space. Now, what's interesting is that it comes with an amazing guarantee. If there exists any hyperplane that separates the positives and the negatives in a given space for a given data set, then it is guaranteed to find the one that agrees with it. If a dataset is linearly separable, then the perceptron is guaranteed to find it. So it was originally published as an online algorithm where exactly one example is processed at a time. So when we discussed decision trees, we mentioned about batch processing where a batch of the input has to be seen at once. That was for decision tree. For perceptrons, these are online algorithms. It is also a mistake driven algorithm where updates are made if and only if it makes a mistakes on an example. So during learning also, we have to understand during learning also, first of all, a prediction has to be done. Then we check whether the prediction matches with the ground truth label or not. And based on that, the loss is computed. So let us say at some point in training, it has the learner or the classifier has seen a particular input and it has made the prediction based on the weight vector it has. Now let us say that came out to be true. It doesn't matter whether it came out to be true because the learning was correct or by fluke. The system has not made a mistake for that instance. So no updates will be made during that case. But suppose for an instance, for an input data point, a prediction is made and that is wrong. So I'm talking about the scenario in training itself, there is a prediction step. And only in training setup only you know the ground truth level. Then only you can compute or you can update the parameters, right? So I'm talking about the training stage where a prediction is made. And let us say there is no mistake being made in that prediction. Then there is no update happens. You go move on to the next data point. But let us say a mistake is made. So if and only if a mistake is made, then the weight vector is updated. How does it do? We will look into the perceptron algorithm. But largely, this is an overview of, say, any classifier, and specifically for perceptron, where we talk about the online algorithmic aspect as well as the mistake driven aspect of it. Again, perceptron is a pretty classical example or a practical algorithm. Perceptron is a classical algorithm which was proposed first in 1958 by Rosenblatt. So several variants of it exist as of now. But now for today, we will look only into the classical one as defined or as described by Rosenblatt. So now you might be surprised that the whole algorithm fits into a single slide. So it's just these 3 steps or maybe a total of 5 steps including the sub steps. And it neatly fits into the single slide. So anyway, let's look into the algorithm in more detail. The input to the algorithm is a sequence of training examples. And let's say the ith instance of the training example is represented as a tuple of xi, yi. Here again, remember that xi is the feature representation of the ith instance and it is a d-dimensional vector. Y is a -1 or +1. So I would say xi, which is in boldface, belongs to a d-dimensional vector and yi belongs to -1 +1. It's a scalar, it's a label, scalar label. The way the algorithm works is that its internal state is its weight vector w. So you can see there is this xi belonging to rd, yi belonging to -1, 1. The internal state vector w0 or the weight vector. So that is the internal state of the algorithm, and it gets updated as we go along with the training. So from the previous slide, we knew that it is mistake driven. So whenever the system is incapable of making a right prediction for a training example, we say that there is a mistake and we say that we are updating the value. Please note that W is also a d-dimensional vector to match that the features vector size of the input. And it is initialized as a 0 vector. So basically all features or all the d dimensions have a 0 value. So the weight vector is initialized as a 0 vector of d dimensions, right? And that's the first step. That's pretty trivial, right? Now second, we start the loop where the examples come one at a time. It's an online learning algorithm, right? So first of all, the first substep of the second or the loop, the second step or the loop is the prediction itself. So first it makes a prediction and assigns it to the variable y dash. The prediction occurs by simply taking the dot product of the input and the weight vector. Here we assume that there is a bias term, but the bias term may be treated as a constant feature and folded into W for the sake of our notational convenience. But in reality, there will be a bias term. So now if the predicted label y dash and the true label, if they are the same, right, then nothing has to be done. We just go on to the next training example. But let's say the predicted label, that is y dash, and yi, which is the true label, they are not the same. That is where the second condition is, right? If they are not the same, then that implies there is a mistake. The true label was yi, we predicted something else, which is y dash. In this case, there are only two labels. So if yi is 1, then y dash has to be -1. And if yi is -1, then y dash has to be a 1 if they are not equal, right? So if the mistake is made anyway, where y dash is not equal to yi, then there is a mistake. And since it is a mistake driven algorithm, the perceptron update or the weight vector gets updated, its internal state or the weight vector gets updated precisely at this point. And you can see the update step here. So once let's not bother about how the update happens or what exactly is happening there for 2 minutes. I will just complete the algorithm and will come back to what happens inside the update. So let us say that the perceptron algorithm is simple 3-step algorithm where we initialize the weight vector or the internal state to be a 0 vector. Then we loop over every training example. For each training example, we make a prediction. If the prediction matches with the ground truth, do nothing, just proceed to the next example. If the prediction does not match with the ground truth, then we make an update. And we continue this process until every training example or whenever a training example comes in and it is completed. This loop is completed only until the training set is exhausted, right? So once that happens, once the loop is finished, we simply return the final weight vector, which is the internal state or the final classifier. So now we will see how the update is happening, right? Update. So at any point, we have a current weight vector. So if it is at the very first point, then also the weight vector is 0. It's a 0 vector. So at any point, let's say at the kth point, assuming there are some updates happened previously, there is some weight vector which we represented by Wt, right? So we have the current weights Wt. We also have the features for the current input, that is xi, right? We have the current feature. We also have the label, which is yi. So we simply multiply the label with the features and further use a constant r to multiply it. So first of all, what we do is that we simply multiply the vector xi with the scalar yi. So basically we are assigning, the yi is either +1 or -1. In this case, we are assigning a sign to every value within the feature vector, and we further scale it. So we multiply, by multiplying I mean it can be a scaling operation. We further scale it using a constant r. And once we have that value, we simply add that to the current weight. Thus the internal state of the algorithm is updated. Please note that yi is a scalar, xi is a d-dimensional vector. So we get a d-dimensional vector after the product with the scalar yi and r. R is also a scalar, it's a constant and it's a scalar. The weight vector is also a d-dimensional vector, and hence the sum results in a d-dimensional vector, which is the new weight vector, which will be used for the prediction for the next training exam. So if the example is a positive example, it basically adding the current example to the current weights with a scalar. So if your input where a mistake was made, and if that ground truth label yi was a positive one, then all you are doing is that we are adding the current example to the current weights. Only thing is that we are scaling it with a value, constant value r. Now if the example is negative, then we are simply subtracting the feature weights again after scaling it with the same constant r. Thus happens the entire updates, and r is the learning rate, or we call as the step size. It is generally a small positive number which is less than 1. And this is how the perceptron algorithm works. So thanks everyone for attending this lecture. For the next lecture, we will look into nearest neighbors, and also into SVM. These are the two things remaining. Until then, thanks.